Hi everyone, thank you. Thank you for coming to this talk about TLBleed. All right, so big picture, we are going to talk about lots of kind of nitty-gritty details about how the CPU works. Oh yeah. About how the CPU works. So we're going to talk about CPU caches, TLB, how to attack other processes through the CPU cache, how to defend against that, and how this new attack vector using the TLB will work to bypass those defenses. So we're going to steal cryptographic keys from another process, not supposed to be possible, using a completely new technique that is not through the cache. Briefly about me, I'm a PhD student in the FUSEC research group at the VU University in Amsterdam. We're an academic group focusing on system security, so we do both exploitative projects, exploitation projects, as well as defensive projects, both on software, and lately also we're kind of dabbling in these hardware attacks. So we use software techniques to exploit hardware properties that give us side channels. If you want to kind of guess what my favorite kind of project is between offensive and defensive, this was my vanity license plate when I lived in Tennessee last year for 6 months. Still proudly in my office in Amsterdam. All right, so overview of the talk is side channels in general. What are they? What can we do with them? The example of side channels in software, which are cache attacks. How can we protect against these cache attacks? There are two different ways. And how does TLBleed fit in that picture? How does it work? What are the properties of the TLB that make this possible? And how well does it work? Let's evaluate this thing, and how did the world respond to this? So first of all, side channels. Super fast introduction. I'll try and keep it short because most of you probably already know about this, but just to set the stage. Side channels is a way to leak information from a system using side effects of how that system works in a way that the designer did not intend, right? So this only works on safes, I think, from the 50s. But if you, the first kind of tumbler safes, you attach a stethoscope to it and you can hear the tumblers fall one by one instead of, so you can break the combination one by one instead of all at the same time. That's only possible because of how the safe works. And this is not what the designer intended. So we can leak secrets from a system like this. The history of digital side channels goes all the way back, well, much farther either, but in public life, in recent memory, it was all about smart cards. Smart cards process secrets sometimes, even if you're the owner, you're not supposed to know the secrets, and as a side effect of processing these secrets, it generates all kinds of signals into the world that sometimes depend on these secrets, and whenever that's true, we can sometimes leak these secrets from the smart card as a side effect of how the system works. It could be power consumption, electromagnetic radiation, execution time, and in some cases even the signals might leak into a speaker, giving rise to acoustic cryptanalysis. So what is the software equivalent of this? These are cache attacks. So normally the abstraction that we're all given and are given to believe is that processors and virtual machines are perfectly isolated from each other in a computer system. One cannot read the memory of the other, and this abstraction is very, very comforting. But the reality is different because there are many shared resources in a computing system that are the RAM chips. We're sharing the RAM chips, we're sharing the CPU cache, we're sharing probably many other resources that we maybe even don't know about today. And all of these, whenever you share a resource like this kind of abstraction starts to break down. This perfect isolation starts to break down. Whenever you share a resource, this practically always allows you to send secret messages, send messages to each other by observing the state of that resource. And then, depending on what you observe, you see that the other party that's also seeing this resource is sending you a message. We call that a covert channel. And also sometimes that allows for leaking information that the other party is not cooperating with, and these things could be secrets. So we call that a side channel. So examples of this is you might share a row in RAM. So RAM is accessed in these structures called rows, and whenever you switch from one row to another, it takes a certain amount of time, and you can observe this latency. So that means that you can observe the access pattern of other processes onto a RAM chip by observing things that only that you can observe yourself. So this histogram shows the latency difference. The same thing goes for shared caches. Whenever all processes are sharing a cache, cache is critical for performance. That's why they're never going to go away until, well, everything changes. And whenever you share a cache, that also means you can observe whenever someone else, another process fills up the cache, because you can see your own stuff is gone from there. And we're going to go into more detail about how that might work later on. All of this is only possible because of shared resources. We're sharing the L1 and L2 cache on a core. We're sharing the L3 cache between all these cores. And because of these shared resources, this kind of spying becomes possible. So let's look at an example. This is all still just background information. It's not my work. This is just an example that sets the relevance for TLBleed. So this cache attack is an example of this is flush and reload. It's very common in operating systems that you actually literally share exactly the same physical memory. It's a very powerful technique to reduce the working set size, because if we're both doing the same thing with the same program and we don't have to copy that because of that, it means we can, there's less copying going on, there's higher cache utilization, the working set size gets less, and everything is faster for these reasons. It also means that you're playing with exactly the same physical memory that the other process is playing with, using. So let's say there's a system call called mmap. Let's say we're using the same cryptographic library, maybe libgcrypt or something like that. We both map them into our own address space and we're using exactly the same physical memory. It means that if I tell the CPU, which I can if I have access to that memory, if I tell the CPU to flush this piece of memory out of the cache and it goes to RAM, and then I access it again, it's going to be slow. But if someone else, my victim, used that memory in the meantime, it's going to be fast again. So that gives us the side channel saying, hey, someone else used the memory, so this perfect isolation is gone. So how does this work? So let's say that we are, of course, the attacker, so we're the lower bar, and the red block indicates reloading, and blue indicates flushing. So the blue operation says, send this piece of memory away out of the cache. We wait a little bit, we try to access it again, and because we send it away, the next operation, the reload in red, it takes a longer amount of time. Unless our victim, which is using the same memory, has used it in the meantime. This makes the second access fast suddenly. So as a side effect of our victim accessing the memory, we see a lower latency on the second access, so that gives us this side channel. And we can do all kinds of tricks with a primitive like this. And there are many more examples of cache attacks like this, which use different mechanisms, which don't require sharing, but this is the easiest to explain. But this is the general principle always. So let's look at an example of an attack that we can do with this. Let's say we have an AES implementation. An AES, of course, uses the secret key. That's supposed to, of course, remain secret. But let's say the implementation has a flaw. Sorry, implementers of this, of this implementation, that uses what we call T-tables. This means that the AES implementation will, in the process of encrypting something, it will look up in a pre-computed table to speed things up. It'll look up something that it needs to generate the encrypted stream, and that thing is a XOR of the plaintext byte and of a key byte. And as you can see from the syntax, what it wants is somewhere else in the table, in other words, somewhere else in memory, depending on what the plaintext byte is and what the key byte is. So if we know what the plaintext is, which is often the case if we feed the encryptor plaintext that we know, like a known plaintext attack, and we observe where in the table we're seeing these accesses, then we can figure out, by knowing what the plaintext is, we can also figure out which key byte was used to generate that access. So we can compute the key bytes. So as an example of how that might work, we here see this coloration. This figure is from a paper called Cloak that uses defense, which we're going to talk about later. We can see a very strong correlation between the activity in a particular cache line and what the plaintext byte is. So that allows us to attack this implementation. So let's see another algorithm that we're going to talk about later in the context of TLB also. So this is, I I won't talk about all the details here because it doesn't matter that much, but the most important thing here is that this is a elliptic curve cryptography implementation in libgcrypt, and I should say this is not the side channel proof version, right? So there's a side channel proof version that is safer than this, and there's even a newer version which is even safer, which we'll also talk about. But let's just, for the sake of illustration, look at this non-side channel proof version. The unsafety comes because of the second conditional here. The conditional here. So the scalar is the secret value. This is a function that might be called when you're signing something. So it needs a secret key, which is stored in the scalar, and then we do this multiplication, which is a series of duplications and conditional additions, and the addition conditional depends on what the secret value is. So we're processing this secret bit. We do duplicate, 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 add, duplicate, duplicate, add, duplicate, add, depending on what the secret is. So let's see that visualized in what might this look like in the CPU cache. So let's see. We're going to see on the top half here, we're seeing the signal in the cache that is reads. So these are data reads. And at the lower half, we see execution. So this is the code accesses. And you can see that the blue is for 0, so it's short, it's only duplicating, and green is for 1, so it's longer. We're doing duplicate first and then an addition. So you can see these signals, they look like a mess, but they're still very different, right? So if we can tell the difference between one access pattern or the other, then we can leak these key bits. So let's put them one over the other and see if we can tell any difference. So here's duplication, there's duplication, and then an adding. So if we can tell the cache signature of this adding part, and I can kind of see some differences, then we have a side channel that can leak the secret key. All using the CPU cache. Now, can we make the algorithm better, the implementation better, so that it's not possible anymore? Yeah, we can do that. We can unconditionally do the duplication and the addition, no matter what the secret key is. We just do both, and then conditionally use the result. So what would that look like? That's a 0-bit, that's a 1-bit. Now this looks much better, right? We can't really tell the difference between one or the other. There's a small exception. If you can spot it, if we look at the green signal, that's a fraction longer than the blue signal. Do you see? Right at the end, there's this tiny little bit of extra operation, and that's the conditional using of the result, because we only want to use the result in the case of a 1-bit, because otherwise the addition should not happen. And in the case of the 1-bit, you can see this tiny little bit of extra work that's done to use this result. And that is also a side channel that we can use. And there's an even newer version of this code, which is even safer, but this is just, so I'm not trying to make libgcrypt look bad here, they're doing a great job. It's just to demonstrate or to show to you that it's extremely hard to do these side channel proof implementations. It's this arms race that's been going on ever since, well, I think 2005, roughly. And new side channel results are still coming out today, and which sometimes depend on the code, but sometimes it also depends on a microarchitectural property of the CPU, which are very hard to predict. So just trying to say it's extremely hard to write perfectly side channel proof code, and maybe we shouldn't even expect to be able to do it. And for that reason, it would be really great if there were generic defenses. Can we just deploy some cache magic that makes even these unsafe implementations unmonitorable, but keep the benefits of the cache? Now that would be great. So let's look at that. I'm going to talk about 3 general ways to do this. One is cache coloring. So the cache looks something like this. All these physical pages have a color. They call it colors. They don't really have colors. Let's say 128 different ones. And every physical page, every blue page, so to speak, will go to the blue part of the cache always. That's just how the cache is partitioned. Normally you don't notice this, but it does mean that if you are trying to access, if you as a process only get blue pages, you can never see any cache activity of a red process. So that's one way to do it. Another way to do it is to use this Intel CPU feature called CAT, Cache Allocation Technology. It partitions the cache in a different way. It was not intended for security, but we could use it for security. It was intended for more predictable performance. If you put a bunch of VMs on a machine and you let them access the cache using a partition like this, it won't make it faster, but it'll make it very predictable because the cache usage is not sort of blocked, not obstructed by other VMs running on the same machine. And then one final example is TSX, which allows you to create memory transactions, also an Intel CPU feature. So we can say, okay, I want to start a transaction, do a bunch of operations, do a commit, and then that will become atomically visible. But the restriction is that in the time that this transaction happens, all of that data must fit into the cache, because as soon as it goes to RAM, we can't undo the transaction anymore. We can't abort it. So that's interesting. Also not intended for security, but it was intended for concurrent programming. But what we can use, we can exploit this because of the fact that whenever someone is playing tricks with your cache, you're going to get evictions because the other side is trying to monitor, is it in the cache or not? And as a side effect of that, the transaction will abort so that the other party will hopefully not be able to deduce any information from that. And just to show you how what the signal will look like, also with flush and reload on the AES attack, remember? This is the original signal, has very strong correlation with it but if the sensitive operation is done inside a TSX transaction, the signal is destroyed. And that's really great, because now we have an unsafe implementation that cannot be attacked, but the implementation didn't have to change. Now that's a really attractive property. This is work from a paper called Cloak, which uses this TSX feature to protect cryptographic implementations. All right, so all cache problems solved. Dramatic pause. So now we have the situation where we would like to have these very generic cache protections, because it's very hard to do a perfectly side-channel proof implementation otherwise. There are things that the compiler might do that will ruin your safety. The compiler might optimize something that depends on the secret. The CPU might do something that depends on the secret that you can't really predict. Even today, it's hard to predict that. But imagine future compilers or future CPUs. So if only we had these generic defenses. Now, so this talk is about, well, even if you have these generic defenses that protect against cache attacks, that perfectly isolate the cache, what about the TLB? Okay, so by a show of hands, who knows what a TLB is? Okay, great. So the TLB is something that caches page table lookup. So this, the way that these process isolations are provided is that all processes have their own address space. And this is kind of but it's, of course it's not real, it's virtual, right? Hence virtual memory. And this is provided by the CPU by these systems called page tables. So page tables, they map the virtual address space of each separate process onto the same physical address, or at least the same pool of physical RAM. And this provides very strong isolation properties and other nice features. But looking up the translation from a virtual address to a physical address is very slow, relatively speaking. So it would take 4 memory accesses before you can do your actual memory access and slow everything down by 5 times if this were to happen every time. Fortunately, we cache this information in this structure called a TLB. TLB stands for Translation Look-Aside Buffer. So that should make you think, well, if the cache is shared and that's dangerous, if that betrays some activity of what this process is doing, then what about the TLB? Could it be that the TLB is shared, and could that betray any activity of what I'm doing? It's very different, because cache is all about data and code and stuff, and TLB is about translation. So I don't know if it applies, but what if it did? So what we know about the TLB is that it has a low level, the L1 is very fast and relatively small, L2 is larger. We know that it's partitioned, this is according to the documentation, we know that it's partitioned into these things called sets and ways. So sets are just like you saw with the memory cache, right? We have blue and red, they're completely separate. So there's a blue set and a red set. And within a set, we have 12 or 16 entries that are just a pool, so that there could be anything in there. But this is a very small set usually. So we know that the TLB has this partitioning, just like the cache does, and that's very important for us. If we want to access the TLB and if you want to monitor its contents, we also want to know, that means we have to know what to expect under normal conditions. We want to know what to expect if we have exclusive access, and what is the difference when someone else is accessing it as well. So therefore we have to know this structure of the TLB. So what can we, how many sets are there, and what is the mechanism that decides this translation goes into this set and that translation goes into that set. But all that stuff's not documented. So let's try and find out. We use performance counters for this. Intel CPU has many performance counters that whenever something happens, basically an event is counted. It could be, and in this case, we're interested in TLB hits, TLB misses, L1 misses, L2 misses. And using counters like that, we can devise the experiment that accesses a bunch of addresses and then counts, did we hit the L1, did we hit the L2? If we do it even more, do we continue to hit the L1 or continue to hit the L2 or miss it? And so we can do this experiment that says, well, let's just assume that for the lower level, it has a linear structure. So that means that page 0 goes to slot 0, page 1 goes to slot 1, and page 16, if there are 16 slots, page 16 goes to slot 0 again. So it's this sort of very natural, round, circular structure. So on that hypothesis, we do this experiment to try and find out how many sets there are and what the set size is. So this is an experiment where the color indicates the number of evictions that we see. So whenever you see purple or dark, there are no evictions, so we can just access all this. We can access our experiment all the time without filling up the TLB completely. But every now and again, we hit this. We do hit these colors, and that means that okay, now we have an access pattern that hits a small number of sets all the time, because apparently we're seeing evictions. So, and that tells us something about what the set size is and how many sets there are. So we see from the graphic that we need at least 4 elements to completely evict a set, right? Because the lowest number of elements that cause evictions is 4. You can see that with the third bar. And the lowest number of sets that we have that can cause this eviction is 16. So that tells us we have 16 sets, and each of them have 4 ways, so the set size of 4. So it's just nice to have this kind of information confirmed, whether it's documented or not. For the L2 TLB, we also did some reverse engineering, and we find out that it's not linear sometimes. So we tried this on Skylake, one fairly recent Intel micro architecture, and we find that this is all about pages, right? So we have to discard the lower 12 bits of the virtual address, and we find that what determines the slot number is not simply the lowest bits, but it's the lowest 7 bits and then the lowest 7 bits above that XOR together, and that determines the slot number. So expressed as a matrix multiplication, this would be the matrix for transforming a virtual address, or a virtual page number, I should say, to a slot number, to 128, to a slot number of 128 a maximum, so 7 bits. For Broadwell, it's twice 8 bits. And all this information is important because if you monitor the TLB, you have to be able to predict what it's going to do. And using this information, we can predict what it does if we're using it exclusively, and therefore we can see the difference when someone else is using the TLB as well, because that's what we want to do. So now that you know the structure, let's see if we can see what's happening, whether we get hits or misses using only the latency. And that's really important. Oh, I skipped a slide, sorry. So let's see if these TLBs are shared or not. So let's look first, we do this experiment. Now that we know the structure, we do this experiment where we access all possible slots, 0 to 16 on one CPU thread, and 0 to 16 threads on a different CPU thread, and count how many evictions we see. And if the TLB is shared, we should see evictions depending on who's accessing what. And as you can see with a DTLB, this L1 DTLB, we do get the evictions that we're expecting. Whenever we access slot 0 on one thread and slot 0 on the other thread, we see evictions, but not in other combinations. So 0 is shared with 0, 1 is shared with 1, and so on. Not so for the ITLB. So we find that the ITLB, which stores these instruction accesses, is partitioned between these two threads. So it's not shared. So we cannot see any code activity from the other thread, which is a shame because that's a very powerful source of information. In the L2 TLB, we also find that it is shared, but interestingly, the slots do not align. So slot number 0 on one thread is shared with slot 64 on another thread. So that tells us that probably in this hashing function that determines the virtual address that goes to a particular slot number, there's probably like an extra bit of information in there, like the thread ID or something like that. And maybe, this is just speculation, but maybe that causes the TLB usage to be smoothed out between threads. Maybe it causes less contention that way. It's just a guess, but there has to be some reason for it. So here's a little summary of all these properties of the TLB that we reverse engineered on as a function of different, looking at different microarchitectures. So what we see, I think the most interesting thing is what is the hashing function? That's for the L1 TLB is linear everywhere. DTLB is shared everywhere. The ITLB is shared nowhere. And the L2 TLB has a huge number of sets. It has, Skylake has 128 sets of size 12 each, which is 1536 entries, which is massive, I think. And these strange, well, I think kind of strange hashing functions that they use, they started using since, I think since Skylake. So I think that's kind of interesting information to know that that's not documented. So now that we know the structure, we can't use performance counters if we're an attacker because that's privileged and too slow. So can we tell the difference between accessing L1 and L2, missing L1 and L2 using only latency? It turns out that we can. So here's a histogram of L1 hits in blue and L1 misses and L2 hits in orange and L2 misses in green. So you can see there's a big difference there. The thing with green is that we have no TLB entry, so we have to do a page table walk. and this page table walk still sits in the cache because all these page table cache lines will be cached still. So we have, we don't have to go to RAM. So, but we do have to do this walk going, well, here's the first entry, second entry, third entry, and that'll just take some time to assemble. Okay, let's try and use this knowledge to attack this not side channel safe function that we found in libgcrypt, just as an example of just to show, can we use the TLB for stunts like this? So again, we see that the secret value of the scalar determines the control flow path. So only if it's 1, we do this addition, otherwise we do not do this addition. And we want to try and tell the difference between one case and the other case, between the scalar being 0 or 1, only using these data accesses, because we don't see any code access because the TLB is not shared. The ITLB is not shared. So can we do this? Well, I don't know. Let's simulate this in just like we did for the cache, but now we use we show what the signal might look like if we view it through the TLB instead of the cache. Okay. So here's kind of a simulation of what it might look like if we're in 16 different TLB sets, and all these things are page level granularity, so it's very, very rough spatial resolution. It's not great. So what we were hoping for is that whenever so green and blue are the secret values, right? The secret values that you don't know as an attacker, but you want to try and find out based only on the measurements that you see. So what we're hoping for is that one set would be active only for green and a different set would be active only for blue. But we don't see that. Every single set is active all the time or never. So that makes our job even harder than it already was. What we do find is that there is a temporal different signal. So there's the signal in time is different depending on whether we're green or blue. Now that's interesting information. So you can see the red rectangles here show you, well, there's this axis pattern that looks like this in the green case and looks different in the blue case. And that's a detection that we might want to do. So this is how this looks. If we were to collect this trace, this is how it would look like. we see, and this is very, very coarse, right? We only have 16 different sets, and the resolution is 4K. So yeah, you can kind of see a difference, but it doesn't look great. So we try and distinguish the blue case from the green case, but what I'm seeing here is sort of a lot of noisy stuff in the same sets all the time. So that looks like it would be hard to analyze, but at least we're seeing something. So what we try to do is then we monitor a single TLBleed set and use information that changes in time instead of in space. It would be much easier to just say, monitor 2 sets and see whenever I see something here, it must be a 1-bit, whenever I see something here, it must be a 0-bit or something like that. But we can't do that because that distinction doesn't exist. There's no spatial separation. So that makes it a little bit harder than the usual cache attack, because usually you can find 2 different cache lines that mean this. So what we try to do is we use this machine learning algorithm. Oh yeah, if you were at the keynote yesterday, you hear Jeff Moss say, kind of felt to me like it was a bit admonishing. Yeah, we use all this advanced technology that we developed. We use them mostly for offensive purposes, like machine learning and stuff. So I don't want to say I'm part of the problem, but we use machine learning for offensive purposes. So we try to, we capture this. This is the raw signal that we capture for real on the SPY thread. So we access a TLBleed set all the time. Most of the time the latency is low because that means that because our sets, the access that we do, it fits in the set completely, fits perfectly, so it's fast. So we know that whenever the latency is high, whenever it's slow, it means that someone else, our victim process, needed to use that set for something. And that tells us something about the activity that it's doing. And we're trying to see what this activity, as you can see, that there's no easy way to make the distinguishation. There's no easy way to distinguish it. But there is this sort of signal that changes in time that can tell us a lot more information. So if you look at the moving average of this latency, then we can start to see these differences. We see that the blue, which is a 0 key bit, we see that the blue has this very regular spiky pattern, and that green looks a little bit messier, but it's noticeably different from blue, right? So we want to be able to distinguish this. So I probably wouldn't write a program by hand, probably couldn't write a program by hand that does this distinguishing, and I kind of don't want to. So can we train a classifier that will automatically classify the 0 secret or the green or the 1 secret given enough training examples? Because we can generate all the training examples that we want, right? We assume that we know the binary that the victim is running and that we know the microarchitecture the victim is running, and that is the only 2 things that that determine what the signal will look like. So we can generate all the training examples that we want. So we use this SVM classifier. It's called support vector machine for those of you who don't know, which works like this. So we give it these green training examples and these red training examples, and then the SVM classifier will try and find this line, this big black line that separates those 2 things. So whenever it whenever it sees a new sample and that it doesn't know what it is, doesn't know whether it's green or red, it uses that line to determine, well, is this a green or a red sample? And this kind of a simplification, because this graphic just shows a 2D feature space. All of the points only have an X or a Y property, so we can plot them very nicely. In reality, that's not enough. Certainly in our case, we're going to use this big signal, which can be, I don't know, it could be like 100 measurements. So we're going to use 100, we're going to give the classifier a 100-dimensional space. And I'm going to tell it, okay, these are 100 samples from one case, this is 100 samples from a different case, can you please tell the difference? So it's trying to find this separating line or plane or hyperplane in our case to separate those 2 training sets that it gets. So let's see how well it does. So we see that after much experimentation, we find that we can train an SVM classifier to tell the difference. And we want it not just to say, when are you blue and when are you green? We want to say, when does blue start? Because there could be multiple blues in a row, and it would be much nicer if the classifier could tell us that. And we find that it can. So it can tell us reliably when does blue start is plotted with 0, when does green start is plotted with 1, and half is, well, nothing's happening. And it gets this done very well. So we see start of this first one here. Why am I pointing at that thing? This first one here is wrong, so it's not the start of blue, but all the other ones are right. So just as an example, it's not completely perfect. Start of blue, start of blue, start of green, start of blue, start of blue, start of green, start of blue. And that leads us directly, then we apply a peak detector that says when is a 0-bit starting, when is a 0-bit starting, when is a 1-bit starting, and that gives us a bit string that can perfectly correspond, well, it perfectly corresponds to our guess of the secret key. That does not mean we're quite there yet, because there could be glitches. We do assume that we can guess, that we can verify guesses of the secret key. That means we can do a little bit of brute forcing if the guess is not perfect, and we find that most of the time we only need a tiny amount of brute forcing to actually get the full secret key. But how good is it? So let's see, we tried 500 trials on these 3 different microarchitectures. On Skylake, Boardwell, and Coffee Lake, we tried 500 times. We find it very high after some brute forcing. How many percent of the time can we guess the right key? Well, it's over 98% using just a single capture trace. That's quite unusual for a text like this, by the way. So using just a single trace, well, first we capture many traces for training. That takes about, the training takes a minute. Then we capture a single trace in the attack mode where we don't know the real truth and do a small amount of brute forcing. And we find that 98% of the cases or more, we can guess the real secret key after just a single trace. And in total, that takes about 17 seconds from capture time to including the classification and including the brute forcing. In the median case, that it takes just 17 seconds. So you can see here that most of the time we need hardly any brute forcing at all. And in some cases, that just means like, oh, it looks like we guessed too many zeros here, we'll take that out, we'll put 1 in here, and then most of the time we can guess it very, very quickly in less than 32 tries. And sometimes we need many more tries, but then at least eventually we can guess it. I mean, 2 to the 30 in the worst case is still much better than 2 to the 256. Okay, as I've been promising you all along, can we bypass cache defenses with a technique like this? And the answer is yes. So we apply this cache defense called Intel CAD, the cache allocation technology. So that, if you remember, is the feature that separates cache sets sort of horizontally, right? So you can only access a part of the set and part of the set. And we find that if we separate the spy process and the victim process using this CAD technology, so they cannot see each other's cache lines, we can still, with a very high success rate of 96%, guess the secret key on the victim process. Okay, so a word about how this work was received. We reported this to Intel. They said, meh, they said we're not impressed, basically. They said, well, yeah, you know what? There's already enough guidance out there about how to write perfectly safe cryptographic implementations. And if they were perfectly safe, it would also be immune to TLBleed. So we see this as not a new side channel attack. This was done on the HackerOne bug bounty program, for which side channels are recently in scope. So we thought, okay, we'll give that a shot. And honestly, I can see both sides of that. It's just not what I was hoping for. Okay. OpenBSD disabled hyperthreading because of this, so or at least by default on Intel, you know. So they committed this a couple of months ago, disabling, because they could see this risk and related risks to TLB and page translation is what made them decide to finally disable hyperthreading by default. As a result, there was lots of media coverage, so we are not usually in the business of making logos for our offensive projects, but the register was kind enough to make one appear on the article anyway, so we thought that was kind of cool. Now we can use this logo. I thought they did a really great job also of capturing what it's all about by these 2 hearts or 2 threads, I guess. I think that was pretty cool. Okay, That's most of what I have to say. Just some credits. I did this work together with Kaveh Zavi and professors. I did this work together with professors Kaveh Zavi, Cristiano Grifida, and Herbert Bos. Some diagrams from this talk were gratefully taken from other work, Flush and Reload, Prefetch, and Drama by these authors. Okay, so what are the takeaways that I would like you to take away from this talk? So, outside the cache, we can still do practical, reliable, and high-resolution side channels that have realistic security results. They bypass currently known generic cache defenses, making it extra hard to rely on both a perfect algorithm and a hedge against imperfect algorithms. And so that's something to keep in mind whenever you make perfectly, if you rely on perfect algorithms or a perfect cache defense, there are more side channels out there like the TLB and probably more resources that can also be exploited that should not be forgotten. So these are our Twitter handles and the group project page. Thank you all for listening. I'm a little fast even, so we have time for questions if you want.
For the support vector machine, could you train it on one configuration and then reuse that training data set on a different operating system or different hardware?
Right. Okay. So the question here is for the support vector machine, can you train on one configuration and then transfer that to a different environment? I have not tried this. I do know that the only two things that really matter for this transferring is which microarchitecture is the victim running and which binary is the victim running. So we do assume that we know that. And I honestly don't know how well it would transfer between microarchitectures. I would guess reasonably well, as long as the TLB configuration is close enough. But we do. Yeah, as long as the hardware is the same, that would definitely work. Hi.
Is Intel's CAT technology meant to separate CPU caches or also TLB caches as well?
Right. So the question is Intel CAT intended to separate caches from between processors, or also the TLB? So no, it's not. It's only intended to separate the caches. It's not a. It's actually a good question because the point of CAT was not for security, but you could think you could abuse it for security. So it was intended for to get more predictable performance. But part of performance, of course, is also the TLB, but for some reason that was not considered part of the partitioning. Does it answer your question?
I would imagine CPU caches are different from TLB caches.
Yes, they are.
That's why I would imagine that CAT is only meant for CPU caches, not the TLB cache.
Yes, that's right. Yes, so this I'm not implying we broke CAT. I'm just saying no, that's not what I meant. So what I just meant is so CAT only applies to the cache, but I just want to super clearly demonstrate. Well, even if you have this cache defense, it would defend against cache side channels, but it would not defend against the TLB attack. That was the part of the story.
Okay. Sorry. Want to ask a question?
I think we have time.
Okay. Then why did the success rate drop a tiny bit?
I was afraid you'd ask that. I don't know. So it did go from, but it went from 98% to 96%. So I thought, well, that still seems pretty high. So I didn't investigate that, honestly. I can imagine, now that I'm thinking about it, I can imagine that the behavior would be sufficiently different. So because you do have less cache available to you, So that might make the behavior of the victim process or the spy process for the matter just different enough, maybe it's a little bit slower, that the signal degrades a little bit. That's something I could speculate is happening.
Thank you.
Thank you.
So maybe one question about, let's say, other platforms, embedded systems, for example, ARM or RISC or whatever. What do you need in the processor structure or in the system structure to make this attack work?
Right, okay. So the question is, are we, what about other architectures and other platforms? Are we, do we see any possibility for it working there, and what do we need for it to work? Did I get that right? So the two things that are necessary for this is concurrent access to a shared TLB. So the TLB has to be shared, and it has to be possible for there to be a concurrent access. And what that will mean is that I don't think there are any architectures out there that have TLBs shared between cores. Doesn't make sense to me. So I think what's necessary is for there to be hyperthreading within a core, so we can have multiple threads of execution active in parallel to some degree, to a significant degree, and that the access to the TLB is shared between those execution threads, and that the concurrent access is possible. So I briefly looked at a new AMD machine for this. It was again? Ryzen, I think. And to my, I couldn't quite get it to work. It seemed like the TLB, and someone told me, and what I saw seemed to confirm this, that the L1 TLB was completely associative. So there's just one big pool of entries, no sets, which doesn't mean the attack would be impossible. But in fact, in some sense, it's easier because you don't have to pick a slot. But the accuracy was very bad. Maybe that has something to do with it. For ARM, I have been trying to find machines with hyperthreading and concurrent access. Seems to be very rare for ARM. Seems to be very rare there are any hyperthreading configurations out there. I found one, which is, what's it called again? The KVM Thunder X2, which is a very expensive workstation model, so I couldn't easily buy it to test. But I am waiting for. I'm talking to someone who can probably arrange for borrowed access to a machine like that, and then I will try that out. There are Spark and Power platforms, which of course have highly threaded CPU implementations, on which this may be possible, but I haven't tried that out.
And talking about, let's say, software countermeasures, I mean, as I understand that the leakage was mostly on this data buffer, not on the instruction TLB cache, right? So if you would kind of obscure the data, masking, for example, or yeah,
yes,
that would basically help, right?
Yes, that would work. So if I understand you correctly, we only observe the data trace of the data signal, and if the data trace would be not dependent on the secret, then it wouldn't work. Is that right? Mm-hmm. Yeah. So you're right. You're right about that. That's the new version of this code that we take in libgcrypt. Does seem to have such a very strong data trace independent implementation, secret independent data trace implementation. But what we argue in this project is that, for one, it's very hard to make these implementations perfectly side-channel safe, because there could be artifacts in your compiler or your CPU architecture that you didn't foresee or didn't know about, and then same thing for future revisions of compilers and CPUs. And therefore, it would be nice to have generic cache defenses. But then this is an example of how these generic cache defenses could be bypassed. So you're right that if the algorithm is perfect, then this won't work. But it's also devilishly hard to make perfect algorithms.
I would agree to that. Thank you.
Thank you.
Would it be reasonable to just say that if you use large or huge page for any compute-sensitive, crypto-sensitive processes, that kind of obviates the whole TLB part of the problem?
So the question is, what would the effect be on large pages in the processor? Is that right?
Well, they're all going to be in the same virtual page
Yeah.
at that point, right? So.
Yeah. Yeah, indeed. So that's true. I haven't tried this, but I would expect that what we see is that all of those signals that you saw in that chart, you'll probably see them all added up, I guess, because you see all this activity all the time. And I would guess it would make it so noisy. I guess it would be very noisy, but I don't know if you could still make a distinguishing some. The signal is in there, so I would kind of expect it would still work, but it would probably be a bit harder to analyze.
But you're just not going to have any more TLB misses for anything related to that process if it's going to be all in the same large page, huge page.
I'm sorry, I didn't catch that. Could you repeat?
If that sensitive process is all running in the same huge page, you're not going to have TLB misses for that one anymore. Probably. Or you're going to have them all at once. Right?
Which situation is this?
You're not going to have small pages level granularity introspection into that process. It's either going to be there or not for the whole execution of it. Anyway, for future research.
I'm afraid I'm not following. Maybe we can talk about this afterwards?
Sure.
Thank you.
Just a final question.
Yeah.
So have you tried this? I think I've seen, you mentioned that you had a Broadwell server, Xeon server, right? Did you have a server where you tried this
Yes, that's
experiment?
right, yes.
Okay, did you try doing this attack while running other workloads
Yes.
that would introduce noise?
Yeah, that's a good question. We did, what we see, because it happens occasionally anyway, so what we see is that sometimes an interrupt might occur or some other process might be scheduled on top of the victim and then the signal is gone, of course. So what we didn't actually quantify this, but just from kind of eyeballing the charts that we see then, we just see a long stretch of zeros. So the spy process just sees sort of perfect accesses because the victim's not running. So if it's interrupted in the middle of this secret operation, then it would chop up the signal so you would see it sort of in parts. So it'll probably be quite hard to stitch that together automatically. I think it would be possible. So I think because the time slices for the secret operation is so tiny that I don't think it'll really distort the signal that much. It'll only kind of chop it up into time, and you'd have to splice that together again. So I don't really have numbers on how reliable that would be, but I think the signal is there if you're willing to put it together.
Thank you.
Thank you. Thank you, everyone.